Hello everyone, myself Mr. Sunil Kumar Singh, graduated from BIT Sindri in 1994 in mining engineering and MTech from IIT BHU in 2000. Presently, I am working as a head of department mining engineering at Bilaspur College of Polytechnic, Bilaspur. I have 20 years of teaching experience. Now, I am going to deliver a speech on natural ventilation. These are the contents: introduction, causes of natural ventilation, direction of natural ventilation, thermodynamics of natural ventilation, determination of natural ventilation pressure, numerical example and references. Now, come to introduction. Natural ventilation in underground mines is without the aid of any mechanical ventilation, that is any mine fan, and this is the totally for natural means. Whenever fan gets closed, then there is a flow of air maintained from intake to return, and this is due to natural ventilation. It is the process of supplying fresh air without using any mechanical system. The external air moves into an enclosed space because of pressure difference arising from natural forces. Natural mine ventilation distributes oxygen from fresh air, which enhances pulmonary and heart function. Some common facts about natural ventilation are as: air flows from a region of high pressure to low pressure. The difference of pressure may be caused by purely natural means called natural ventilation, or by a fan called mechanical ventilation, but natural ventilation is totally different from mechanical ventilation. Small and shallow mines are sometimes ventilated by natural means. Ventilation only through natural means is usually poor, fluctuates to a large extent and subject to reversal of direction. In case of emergency such as fires underground, mechanical ventilation is more effective. However, natural ventilation does play a role in all mechanically ventilated mines. Basically, natural ventilation pressure is not enough to provide sufficient air inside an underground mines. Basically, it is pure by natural means, and the requirement of quantity as well as pressure in underground mines is very high, owing to number of people or number of workers working in the mines is very more, and as per regulation sufficient air should be provided, which cannot be possible through natural ventilation only. Now, we come to causes of natural ventilation. What are the different causes of natural ventilation in underground mines? These causes include temperature, moisture content of the air, barometric pressure, addition of gases, leakage of air, circulation of refrigerated air in deep underground mines, and some other factors may also be considered for natural ventilation in underground mines. Now, come to temperature. Natural ventilation is caused by difference in densities of air in upcast and downcast shaft. Through downcast shaft, intake air enters the mines, and through upcast shaft the return air comes out to the surface. If there is the pressure difference maintained between the air in downcast shaft and air in upcast shaft, there will be a flow maintained from downcast to upcast, because the heavier air sinks down and the lighter air moves up, thus setting up an air current. The difference in air densities is mainly caused by the heating of air in the mine working due to the addition of heat from rocks, main, machinery, light, spontaneous heating, etc. Auto compression in downcast shaft changes the air density according to theoretical relation, and due to this the downcast air becomes hot and becomes lighter. So, they have tendency to flow downward. Now, come to moisture content. As moisture is lighter than air, that is why addition of moisture in the downcast shaft decreases the density of air, because the moist air is lighter than dry air. Presence of moisture also causes evaporative cooling of the downcast air and consequent increase in its density, which adds natural ventilation. Basically, moisture content causes the decrease in density, and density decreases, there is frequent flow of air through the shaft. Now, come to barometric pressure. Barometric pressure means natural atmospheric pressure. It is well known that air density is a function of barometric pressure. If the mean barometric pressure of the downcast air column is higher than that of upcast air column, it helps natural ventilation and vice versa, because the flow is possible only when there is the difference of pressure maintained between 2 points. So, in upcast shaft and downcast shaft, if there is a difference of atmospheric pressure, naturally the movement of air can be enhanced and can be increased, and it is a vice versa, because whenever the reverse process takes place, that is, if downcast shaft is at low atmospheric pressure and upcast shaft is at higher atmospheric pressure, then the reversal of air current may take place, because the pressure difference maintained between the two shafts. That is why due to natural ventilation, there may be a chance of reversal of air current. Addition of gases. Some light gases, just like methane, which emit from underground working in coal mines, which when mixed with air reduces the density of return air, and thus return air density is less, then it becomes lighter, and lighter air moves up and natural ventilation comes into role. Addition of compressed air from exhaust of compressed air machinery used underground has effect on the density of air, because the compressed air has more density, and when it mixes with air, it gives the natural density of air to be high, and which may cause reversal of the direction of movement of the air flow, and that is why there may be reversal of ventilation. Leakage of air in multi-level mine, where the working is in different level, leakage of denser downcast air to the upcast causes an increase in the density of upcast air, thus reducing natural ventilation. It is well known that the density of upcast air becomes high, then there may be a decrease in natural ventilation because of higher density in upcast shaft as compared to downcast shaft. In view of the low efficiency of natural ventilation of the order of 1.4 to 1.6%, it is important to minimize leakage of air from downcast to upcast shaft in order to get maximum benefit of natural ventilation, because leakage always reduces ventilation either through natural ventilation or through mechanical ventilation, because leakage causes loss of air flow and it also reduces the pressure, and reduction of pressure means reduction of flow, and particularly in view of natural ventilation, the reduction of pressure causes less natural ventilation. Circulation of refrigerated air. This is basically caused through deeper shaft, deeper mines. In deep mines, due to geothermal gradient, the temperature is very high, and in order to maintain the temperature at a natural value, the refrigerated air has to be circulated through the mines, and refrigerated air through downcast shaft increases its density of downcast air, and due to this the downcast air has a tendency to move at faster rate downward, and hence this causes the movement of air through upcast shaft, and a natural ventilation gets maintained in those mines. In some of the deep and hot mines, the natural ventilation is very high, because the hot air has tendency to move up, and they choose a path through upcast air, and if their movement is very high, this means the movement of intake air through downcast shaft becomes also high. Other factors means presence of fire in any one of the shaft heats up the air which has then less density. That is, if there is a fire in upcast shaft, it means the air becomes hot and light, and due to this air moves upward and thus adding natural ventilation. But if there is a fire in downcast shaft, it means the downcast air becomes lighter, and which has not a tendency to move downward in easy way, and that is why the natural ventilation becomes disturbed and becomes lesser. Having steam pipes or steam purposely introduced in upcast shaft help natural ventilation, because of decreasing upcast air density, and it has clearly seen that if the difference in density between two shafts is considerable amount, then the natural ventilation occurs, and which adds the mechanical ventilation, because of the pressure is very high, and due to high pressure there is the flow of air through the mines, and which is maintained continuously. Now, we come to direction of natural ventilation. Direction means the direction from intake to return or from return to intake. The direction of natural ventilation basically depends mainly on the depth of the mine, as the depth mainly controls the amount of heat added to the mine air. In shallow mines, where the underground mines is not very high underground temperature, the surface temperature is the major contributing factor to the direction of natural ventilation, because if the surface temperature is very high as compared to underground temperature, there will be natural flow of air from surface to underground. But in case of deeper mines, it is not so much considerable, because deeper mines has higher temperature as compared to surface. In analyzing the direction of air flow resulting from natural ventilation in simple circuit, the following procedure and observations should be noted. First, visualize column of air of equal height between two horizontal datum lines in order to compare the pressure difference between points in the circuit. If both the shafts are at the same level, then the balance of change in elevation between intake and return, the column should extend between elevations of highest and lowest points in the mine. Consider the surface temperature in winter to be colder than those in the mine, and vice versa in summer, unless information to the contrary is available. This means during winter the outer atmosphere is colder as compared to mines, then the air has tendency to flow from mines to surface. Thus, this is the reverse in case of summer. In summer, the surface temperature is high as compared to mine temperature, and there will be the flow of air from surface to underground. So, there may be a reversal of natural ventilation during the weather, that is, if in winter it is from mines to surface, then in summer it is from surface to underground mines. The colder column of air, the one having the lower average temperature, is the heavier one. Naturally, the colder air will be heavier and will from heavier column towards the lighter column. The direction of air flow is maintained. The outer air flow simultaneously into the caverns of the earth, and when it can pass through them it comes out again. This, however, comes about in different ways, for in spring and summer it flows into the deeper shaft and finds its way out of the shallower shaft, but in autumn and winter it enters the upper tunnel of the shaft and comes up to the deeper one. This change of flow in the air current occurs in the temperate region and at the beginning of the spring and at the end of the autumn, because at the beginning of the spring it becomes summer and at the end of autumn it becomes winter. So, there is the reversal of natural ventilation and its direction gets reversed in the two seasons. Now, come to thermodynamic approach of natural ventilation. This approach has been developed by Hinsley in 1950-51. According to this, the mine ventilation system can be compared to a heat engine with the following cycle. Air descending the downcast shaft undergoes auto compression, as a result of which its pressure and temperature increases and a specific volume decreases. Because due to auto compression there is the addition of heat, because this is adiabatic process as it takes place very faster rate, and due to this the temperature becomes higher. Again, as air travels through the mine working, heat is added from rocks to the hot and compressed air, thus increasing its temperature. As a result, its specific volume increases, but pressure decreases, because air becomes light and lighter air has low pressure. In underground mines, there are so many sources of heat, and these sources of heat causes the heating of moving air, and moving air becomes hot and becomes lighter and its pressure gets decreased. In upcast shaft, auto compression, auto expansion takes place, and that leads to increase in its specific volume, but pressure and temperature becomes low, because due to auto expansion it is also adiabatic process. Due to expansion the pressure and temperature gets decreased. Finally, heat is rejected by the air to the atmosphere, and the air returns to its atmospheric condition, becomes initial condition of pressure, a specific volume and temperature, thus completing the cycle. This means air enters the mines, gets its temperature and pressure increased. Again, in mines underground working, its temperature increases, but pressure decreases. Again, in upcast shaft, its pressure increases, temperature decreases, and again it reaches to the normal point at the outside atmosphere. Adiabatic process occur in shafts, and expansion occurs at constant pressure through the workings, as it has been seen by PV diagram. This diagram is indicator diagram, and mine ventilation system should work according to such a diagram in terms of natural ventilation. The work of natural ventilation, let there be a unit mass of dry air which enters the downcast shaft. This unit mass of air undergoes auto compression in the downcast shaft and there is no exchange of heat between the walls of the shaft and the air in the adiabatic process of auto compression, and temperature increases, which can be represented by the graph shown. This means in auto compression it is very fast process. This is adiabatic process. There is no exchange of heat and its pressure increases and naturally temperature increases. This is the PV diagram for completely showing the cycle of natural ventilation process of air flowing through the mines, that is from surface through the downcast shaft, through the whole workings of the mines, and from the upcast shaft to the air and returns to its original position. This has been clearly shown on the graph. Thermodynamics of natural ventilation. In the downcast shaft, the flow work of air entering the shaft, this is shown by W equal to P 1 V 1. This is area O V 1 A P 1. P V, P pressure into volume, is called work done. The work done on the air by auto compression. In the downcast shaft, as air gets auto compressed, this means work is done on the air, and this is shown by integration of 1 to 2 P d V. This is shown by area V 1 A B V 2. Again the work associated with kinetic energy when the air is leaving the shaft, this is shown by W is P 2 V 2. This means new pressure P 2 and new volume V 2, and this is shown by area O V 2 B P 2. Therefore, gross work done on the air in the downcast shaft is the summation of these three work done. This means P 1 V 1 plus 1 to P d V minus P 2 V 2 equal to minus V d P. Again next, in downcast shaft, the flow work of air entering the shaft, this is minus V d P. Subscripts 1 and 2 represents condition at the downcast shaft top and downcast shaft bottom respectively, that is air entering the mines at the through the downcast shaft, initial pressure is P 1, initial volume is V 2, but at shaft bottom its final pressure is P 2 and final volume is V 2. This is indicated by the symbol P equal to absolute pressure of air, V is a specific volume, that is volume per unit mass. Therefore, in downcast shaft work done is minus 1 to 2 V d P. This is area P 2 B A P 1. Similarly, work done in the air in the mine working is shown by area P 2 B C P 3, and in similar lines the work done on the air in the upcast shaft, this is shown by area P 3 C D P 4. Here steps 3 and 4 gives condition at the upcast, shaft bottom and shaft top respectively, that is at bottom of the upcast shaft the pressure is P 3 and volume is V 3, whereas at top of the upcast shaft the pressure is P 4 and volume is V 4, and then total work done is work done in downcast shaft plus work done in working plus work done in upcast shaft. This is finally area of A B C D. P 1 is taken as equal to P 4, since upcast and downcast shaft tops are assumed at the same elevation and they are in natural air. So, P 1 and P 4 becomes equal. Now, we come to determination of natural ventilation pressure. Natural ventilation pressure can be obtained by many ways. One way is from PV diagram. Accuracy of determination of natural ventilation from PV diagram of the mine depends on how accurately the PV diagram is plotted. This depends on the measurement of pressure and volume of air flow at the different points inside the mines and shafts. The actual cycle for a mine with natural ventilation only shown in figure. This is the figure. The pressure difference between points 2 and 3 is equal to the natural ventilation head Hn, neglecting head loss in shaft. If this graph is plotted carefully and accurately, then we can determine the natural ventilation very precisely. Determination of natural ventilation from pressure and quantity measurements with fan running and fan stopped. Clearly, when fan is running, there will be combined pressure, that is Pf plus Pn, which is Rq1 square. Here R is the mine resistance and Q1 is the quantity of flow during the working of fan. When the fan gets stopped, then it becomes Pn, because fan pressure vanished and only natural ventilation pressure comes into role. This is Rq2 square. R is same, but Q2 is the flow caused by natural ventilation, and from both equation we can calculate Pn equal to Pf Q1 square by Q1 square minus Q2 square. Here Pn is natural ventilation pressure, Pf is fan pressure, Q1 is quantity of air flowing with fan running, and Q2 quantity of air flowing when fan gets stopped. Now, from fan pressure and quantity with fan running at two different speed, fan is run at two different rotational speed, and we can say that the quantity of air flow through the mine depends also on the speed of the fan. Naturally, the speed is more, quantity will be more. So, in this case the two speeds are N1 and N2, and R is the resistance of the mine. Then Pn plus Pf1 equal to Rq1 square, and equation 2 Pn plus Pf2 equal to Rq2 square, and from the two equations we can determine Pn. Pn means natural ventilation pressure. As we can see, the formula Pf2 Q2 square minus Pf1 Q1 square divided by Q2 square minus Q1 square. Now, an important term is called motive column. Motive column is, in case of natural ventilation, it is the excess weight of air in downcast air column, which gives to the natural ventilation pressure. It is also called the height of this excess weight of air column in downcast shaft 1 meter square in cross section, which gives rise to natural ventilation pressure, is motive column. It is the unbalanced part of whole downcast shaft 1 meter square in cross section, that is that part of the downcast shaft which is not balanced by the air in upcast shaft. This is the air column, means height, unbalanced height of air, and using the formula P equal to rho G H, this means rho is the density of air and G is the 9.8 meter per second square and H is the motive column, and due to this we can calculate natural ventilation pressure. This is the formula for natural ventilation pressure, H equal to Tu minus Td divided by Td into D. Tu is the average temperature of upcast shaft, Td is the average temperature of downcast shaft, and D is the depth of shaft, and natural ventilation pressure is the motive column into density of air into G. Its SI unit is Pascal. Now comes to numerical problem associated with natural ventilation. We see the question is the quantity of air going down a downcast shaft is 900 meter cube per minute. The surface main ventilator develops a pressure of 500 Pascal. When the fan is stopped, the air going down the downcast shaft is 300 meter cube per minute. Calculate the natural ventilation pressure. Now, solution is let P n be the natural ventilation pressure, then by P equal to R cube square, we have 500 plus P n equal to R into 900 square, that is fan is running, again using P n equal to R into 300 square when fan is stopped, and solving this we can calculate P n, that is the natural ventilation pressure, and solving we can get natural ventilation pressure which is equal to 62.5 Pascal. Again new numerical is a downcast shaft is 465 meter and the average temperature of the down going air is 30 degree centigrade. The upcast shaft has equal depth, but the average temperature of air in it is 37 degree centigrade. Naturally, the upcast shaft air, the air temperature is high. Determine the natural ventilation pressure due to difference in the temperature of the two shafts, as air passing through the downcast shaft is 100 meter cube per second, assuming average barometric pressure in the downcast shaft to be 750 mm of water gauge, another unit of pressure. This is the case of natural ventilation. The flow of air from downcast shaft to upcast shaft due to difference in temperature of the shaft. We determine the motive column. H is T u minus T d by T u into d, and this is 310 minus 303 by 310 into 465 meter. This is called 10.5 meter. Now, density of air in downcast shaft, it is used by another formula 0.4645 B by T d, and calculated value is 1.15 kg per meter cube. NVP natural ventilation pressure is motive column into density of air into G, and with this formula we can calculate the natural ventilation pressure is 118.45 Pascal. And another equation is the fan running at different speed. A fan running at 31.4 radian per second 650 Pascal, fan running at 34.5 radian per second 715 Pascal. Quantity is also different. Next. And we can see the using this formula R equal to P f plus P n by Q 1 square equal to P n plus P f 2 by Q 2 square, and using this formula you can determine the natural ventilation pressure.